Hello everyone, good day. We are at the last week of this introductory field geology course. This is the 4th week and we will have 3 lectures in this week, lecture 15, lecture 16 and lecture 17. The last week, that is the 3rd week, was little longer, so this week would be little shorter to compensate the overall time of this course. In the first lecture of this week, that is lecture number 15, we will see a few brittle deformation that we have observed in and around Ghatshila. At the very beginning, we will show you a very special type of lineation that we did not show you in the first couple of lectures. These are slicken lines, and we will also see the slicken side surfaces as well. Then we will talk about a brittle shear zone where we will see tensile gushes or inertial or sigmoidal fractures, and we will do some analysis through this. And then we will see conjugate shear bands, how to determine them, how to look at them, and what are the different orientations of the principal axis of stresses we will see after that. Finally, we will conclude this lecture with some very important cross cutting relationships that we see in brittle shear zones, and we will see interactions of primary layering, that means S0, and then multiple fractures, how they are interacting with each other, offsetting the other markers, and then how to evaluate them chronologically. With this, we will finish this lecture 15. In lecture 16, we will take you to the Shingbum shear zone. Unfortunately, we could not show you the details of the Shingbum shear zone, though it is spectacular because we could not get access to the exposures that we wanted to go. However, we will show you some parts of it, and then we will move to one of the very important field structural geology aspects, that is strain analysis. We will do strain analysis from deformed conglomerates and deformed convolutes. And with this, we will go to few other cases and we see few more things, and finally we will end lecture 16. In lecture 17, that is the last lecture of the 4th week and also overall last lecture of this course, I will try to give you a very general overview of this area. So, we will use different maps and different data that we have gathered, and we will first try to make an interpretation in the sense that we will make it very general in 2D maps, and then based on that we will slowly try to see what are the 3D interpretations in and around Ghatshila in terms of structures. So, without wasting much time, let us move to lecture number 15. In structural geology, we classify the lineations in 2 different segments. In one segment, we have non-penetrative lineation, and in another segment, we have penetrative lineation. The non-penetrative lineation is essentially confined along a particular surface. So, in this case, we are going to show you one very important non-penetrative lineation, which we see generally on the fault surface. So, imagine this surface and this surface, these two are horizontal surfaces, and this block has moved down with respect to this block. So, this is the fault surface. Now, on this surface, this point was initially here and it has moved now along this plane. So, it creates some linear features along this fault plane, and these linear features are known as Schlichten lines, which is a kind of non-penetrative lineation. And the surface, the fault surface where you have Schlichten lines known as Schlichten sides. Other than these linear features on these fault surface, in most of the cases we see some steps which generally are almost perpendicular. These are the steps they are orthogonal or perpendicular with respect to the linear feature. So, if I make a cross section along this, you actually see it like this. Okay. So, these are the steps you are looking at here from plan. Now, if you rub your palm along the fault surface, then in one way if you go from this side to this side, you will feel that these steps are there and the surface would appear to you very rough. But in this case, if you move from this side to this side with your palm, you will find this surface is smooth. Therefore, these steps and which way they are occurring tells you the movement direction of the fault on this fault surface. So, the movement was along this linear direction, and the movement direction in this case is this on this fault surface. So, we have just seen on the sketch that how does Schlichten side surface do form, and also the formation of Schlichten lines. And here you have two examples to observe. These two surfaces are the Schlichten surfaces. Why? Because we see this surface is smeared with a material which is in this case some quartz vein materials, and this is the slip surface, or in other words this is a fault surface. And on this surface, or even on this surface, if we observe, we see that some linear features going like this. You also see them here making the same trend. These are Schlichten lines, and these lines mark the movement directions of the fault. In addition to these lines, this surface is also characterized by one important feature that I said, the steps on the fault surface. So, what you see here, that along almost perpendicular to this Schlichten lines, you have some steps, and if I move my palm in this direction, I feel these steps. Here as well you have a big step here, it stops, then comes here and so on. But if I move my hand from this side to this side along the Schlichten lines, I see this feel is very smooth. So, that tells you that the fault movement was from this direction towards this direction along the Schlichten line, and in this case as well the fault moved from this side to this direction. So, in summary, this is a fault plane or a slip plane which is characterized by some features. One feature is Schlichten line that gives you the movements of the fault blocks passed to each other, and then these steps inside the or on the fault plane tell you the movement direction. So, in this case it is in this side. There is also one important point to note, as we classified lineation into different broader classes, that penetrative and non-penetrative. You can see that these lineation Schlichten lines are essentially confined on fault planes. Here, here, here you do not see them. Therefore, these are non-penetrative lineations and you can only see them on fault surfaces. So, here this is the trace of the fault and the movement was like this. So, this block moved up with respect to the block here. So, this is the hanging wall, this is the foot wall, and that is the fault plane. This is a contact metamorphic zone. What do you see here? That is the dike, dolerite dike, and in this side we had the country rock mica schist. So, this is the northern side, and at this contact between this mica schist and this dolerite dike, this little tiny thick area about few centimeters, because it is also down a little bit more, this is the contact metamorphic zone or baked zone because of the intrusion of the dolerite dike. What is interesting to look here, that along this contact zone amphibole grains have formed all along and they define a lineation here. From the theory of brittle shear zones, we know that inside the brittle shear zone we form a set of shear fractures, and these shear fractures could be synthetic or antithetic with respect to the bulk shear direction. We also form a set of tensile fractures. So, let us see how does it happen. Imagine this is the boundary of a brittle shear zone and consider that the shear sense here in this case is sinistral. So, if I have a circular marker here, then because the sense is sinistral, the instantaneous strain ellipse would look like this, where this angle is 45 degree. So, this line is parallel to the bulk shear direction. So, clearly we see that this is the maximum stretching direction and this is the maximum shortening direction. As a result of this instantaneous strain ellipse that we form here on this surface, all materials would tend to flow in this direction, and at the same time because of the shear they will rotate counterclockwise. Therefore, on this section if we look, we form, because it is flowing in this direction and in this direction, we will form tensile fracture making an angle of 45 degree with respect to the bulk shear direction, keeping a parity with the instantaneous strain ellipse. So, these are the tensile fractures that one can form in a sinistral shear zone, sinistral brittle shear zone, and this angle is 45 degrees when they form. Other than this, we have two sets of riddle shear fractures. So, if this is the central line of the shear zone, one would be at low angle. This angle makes around 15 to 20 degrees. The shear sense here is synthetic. It would make also another set of shear fractures. This angle is almost 75 degrees to 80 degrees. Here the shear sense is this should be dextral, that means antithetic to this. In a symmetric form, so this is known as R1 and R2, low angle and high angle riddle shear fractures. Exactly similar you will form in this side as well, in this quadrant and they are known as X and P shear fractures. I am not drawing it here, you know it from the theory class. Now, these tensile fractures, if we particularly focus on them, they form eventually with progressive deformation, because we are considering now instantaneous for this time, but with progressive deformation, as I said, that materials in this kind of kinematic feature, they will try to rotate counterclockwise. So, these fractures would rotate counterclockwise and slowly tends to be vertical or even in the other side of this shear zone that we are talking about. But the shear strain is still going on. So, instantaneous strain ellipse would form at each and every increment, and therefore, they would always also continue developing at 45 degrees. And this interaction form a very interesting tensile structure, tensile gashes actually in brittle shear zones, and these are known as sigmoidal structures. So, we will see now slowly how does it happen. Now, if you focus a particular shear fracture now, and our kinematic sense is same, that is sinistral, then let us draw a particular ellipse and imagine that this is the tensile fracture. So, this is the shear plane, trace of the shear plane, where the sense of shear is sinistral. As a matter of fact, because of the sense of shear is sinistral, this will tend to rotate anticlockwise, as I said. So, in the next segment, if I still continue this, the shear plane, the shear fracture has slightly rotated back and it would continue rotating. So, if we still continue it rotating, I am just leaving the edges out for a particular reason, it will still rotate because shear is going on. But shear fracture would also continue to grow and develop, but they will always track the instantaneous strain ellipse and they will always follow this -45 degree orientation. So, here because a fracture has already developed, they will develop at the tip and they will maintain the angle 45 degree with respect to the bulk shear plane. So, here it will take a shape of like that, and eventually the tensile fracture would take sigmoidal shape. With further rotation, you may consider that it grows like this. Now, if you see this kind of arrays and which are common, you must have seen them also in textbooks or in many places in the internet or any teaching materials. And if you just see this, sometimes we are confused that what is the sense of shear here, but from this demonstration you now can understand that we do not have to look at the orientation at the middle, because we know now that they are rotated. It is always this segment. You always follow the tip and we know now that the tip is essentially following the instantaneous strain ellipse, and therefore, if we can measure this and then pass a line which makes an angle of 45 degree, that is your shear plane, and if it is in this direction, the shear sense is sinistral. If it is opposite, then again you do not have to consider any of this section, you consider only this part, and this is a tensile fracture. So, you know that in this case this is the tensile direction. So, your instantaneous strain ellipse was like this, and therefore, the shear sense is dextral. We will see now in this field in the dolerite dike particularly an exposure of this very typical tensile fractures that got rotated to form tensile gashes, and this exposure is exactly right here. We see here a beautiful array of tensile fractures, and as I have just demonstrated, you can see there are 1, 2, 3, 4, 5, 6 of such fractures, and I believe you also can see that the tip of these fractures are curved and essentially giving a sense to you of sigmoidal shape. So, now how to evaluate it? First, how to understand that what is the sense of shear and so on. So, to do that, first task is more or less figure out the middle point of each fractures, and then imagine a line along this middle points, and that would give you the traces or trace of the shear plane on this exposed surface. Once we have this, we can understand the trace goes like this. Then we see the last point is somehow this, and therefore, we can understand that it is moving in this form, and the trace is in this, and this angle versus this angle makes almost 45 degrees, and therefore, here the sense of shear is essentially sinistral. From this beautiful exposure, we can understand a lot of things about the brittle deformation inside this dolerite dike in Ferryghat. So, in this cliff which is almost vertical, and the rock type, as you can see, this is quartzite, and you can see the extreme of brittle deformation that happened here. One major feature that you have already observed, I believe, is this dike, quartz Van Dyke, which is vertical, and on the top of that you also have noticed probably two sets of conjugate shear fractures, and these shear fractures are very important in understanding the late stage orientation of principal axis of stresses. The practice of evaluation of this principal axis of stresses from conjugate joint sets, as I said, is very common, but we are not going to do this here. In the next segment, we will go to another place where the joints have also formed in quartzite, but they are very closely spaced joints, and we can actually see them in a better way, and we will demonstrate the analysis there. So, Rajiv will show this for you.
Here we are again seeing conjugate joint planes. So, this is one set of joint plane here, 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 and we are seeing another set of joint plane which is actually like this, oriented like this and this. These are two sets of conjugate joint planes. We have taken the data of all these joint planes, the attitude of these joint plane and the attitude of this joint plane. So, as we know that from this conjugate joint planes we can estimate the stress regime of this region. From qualitatively we can say that this joint set and this joint set is making acute angle in this side, acute angle in this side and obtuse angle in this side and obtuse angle in this side. So, from our theory lectures in structural geology, what we know that the principal stress, that is sigma 1, should be acting like this. So, the principal compression direction is like this and sigma 3 should be acting from this direction and this direction. So, this is sigma 1 direction and this is sigma 3 direction, and the intersection point of these two joint sets, if we pass a line from the intersection point, that will give us the sigma 2 direction of this entire region. So, this is how we can estimate the stress regime of this local region or the tectonic deformation phase of this region from these joint sets.
Here we are observing a surface where we can see traces of different joint sets, and we can see that the different sets of joints interact with each other, and we can see the intersection angle. Suppose here you can see this is one joint set, this is another joint set, this is another joint sets, and this joint set and these joint sets making an angle here. This is the acute angle and this is the obtuse angle, and we know from the theory classes that acute bisectrix is the direction of maximum compression and the obtuse bisectrix is the direction of minimum compression or extension. So, here we can see that this is the acute angle and this is the acute bisectrix. So, this is the direction of sigma 1, and here you can see this is the obtuse angle. So, here it is the obtuse bisectrix. So, this is sigma 3 and the sigma 2 acting perpendicular to this plane, which is also perpendicular to both sigma 1 sigma 3. So, this is the direction of sigma 2, which is perfectly lying along the joint plane.
So, in this little exposure, we see a number of things. One is the compositional layerings. So, though this rock is quartzite, but we still see some variations of composition, and from this you can tell that this is the traces of the bedding plane on this horizontal surface. Second observation that is very prominent is some quartz veins which are like this and are almost parallel to the bedding plane. So, north direction is this way. So, traces of the bedding that you see here, these are at 62 degrees, and then we see two sets of conjugate shear fractures. This one which is oriented at 120 degrees and this one which is at north south. Now, if I examine this particular area, we see that this is one trace of conjugate shear fracture and this is another trace. Clearly, this is the acute angle and this is the obtuse angle. Therefore, the compression direction is like this. So, this way and this way. If so, then tensile fractures should form in this direction. Okay. That did not happen here. We see the quartz veins which are essentially product of tensile fractures. These are oriented exactly opposite. So, that is kind of a puzzle or paradox. If I have compression in this way, then how these quartz veins are oriented in this form which are essentially tensile. Otherwise, the tensile fractures should be in this orientation perpendicular to this. To solve this paradox, it is important that once we make all these observations, we look for some other clues to justify the orientation of this. And we see clearly in places, for example, here we see there is an offset of this quartz. We see an offset here as well. We see offset of the bedding planes. So, that tells that of course, beddings, traces of the beddings and their solidification was the primary, and then this quartz vein formed, and after that we had the shear fractures. So, this is a very simple demonstration of looking at overprinting relationships and also some little observations if you make here, here and here, that tells you clearly the history of the deformation of this particular exposure.
Thank you. So, with this I end lecture number 15, and in the next lecture we will go to Singhbum shear zone and do some strain analysis, and then we will again come back to Ferighat and do again some strain analysis with the convolutes that we have seen in the first and second weeks.